Hello, welcome back to Chem 4. We are recording lecture number 7 now. So we are in chapter 4, and about halfway through, we are ready to talk about the atom. So we mentioned, basically gave you the definition of what an element is. We mentioned, an element is something that's made up at a fundamental level of atoms. And now finally, we're going to actually talk about what an atom is. So an atom, to give you the strict definition, is the smallest particle of an element that retains the characteristics of that element. So we've already mentioned that, kind of the central thesis of chemistry is that all matter is made up of atoms. And atoms are these very, very small particles, and they come in different flavors. And those flavors are described on the periodic table. So like, for example, with aluminum here, if we could, get a submicroscopic view of what makes up aluminum, you'd see these little, roughly balls, I guess we'll call them. We kind of describe them as spheres, even though that's kind of imperfect. We can just easily think of them as these very, very, very tiny balls that make up all matter. And an atom of aluminum would be different from an atom of oxygen, for example, or carbon or something like that. So each atom has its own distinct characteristics, and that's what's responsible for the difference in matter. Okay, so now we haven't always known that there were atoms. That was a theory that was developed over the 18th century into the early 19th century. The person credited with atomic theory, modern atomic theory, is John Dalton, who was a Quaker priest in England. And he, at the time, basically the only people who could be scientists were people who had some system of support. So like in France, for example, you get a lot of these nobles who have a lot of money from their estates, from their families that are passed down a long, long time. John Dalton was a priest, so he had a lot of time to think and correspond with other scientists. Because he was, supported by his church in that way. So that's kind of why we see, certain names pop up and other names just don't pop up in the scientific history that we do study here. So yeah, John Dalton developed this atomic theory to help understand the other theories that we knew at the time, which was we knew from Antoine Lavoisier in France that mass was conserved in chemical reactions, right? That's the law of conservation of mass. And even though the substance changes, we know, oh, it's the same mass before and after. Also, people noticed, and John Dalton gets credit for this as well, that some compounds were made up of elements in certain proportions that was measured by mass. So, for example, they always knew that water was 12% by mass hydrogen and 88% by mass oxygen, no matter the source of the water. We call that the law of definite proportions. John Dalton combined this understanding to say, okay, there's got to be some kind of discrete way that these are combined that gives rise to the compound that we understand. So he came up with the hypothesis, and backed it up with his evidence that it was atoms that was responsible for this. So here's the atomic theory, and you'll need to know this for the test. Part 1, all matter is made up of tiny particles called atoms. Number 2, all atoms of a given element are identical to one another and different from atoms of other elements. So hold on, let me put our little asterisk here. I'm gonna put an asterisk next to this one for a reason we'll talk about. Number 3, atoms of 2 or more different atoms of 2 or more different elements combine to form compounds. A particular compound is always made up of the same kinds of atoms and the same number of each kind of atom. And then finally, a chemical reaction involves the rearrangement, separation, or combination of atoms. Atoms are never created or destroyed in a chemical reaction. Now, I wanted to put this asterisk next to number 2 and make sure that you put this in your notes. This is not precisely true nowadays. Like, this was a pretty good guess back then, and it is pretty close that all atoms of a given element have very similar properties, but they are not always identical. This is something we'll talk about towards the end. You can just write this word here, and we'll just kind of come back to it later. And it is the isotope. So we'll explain this at the end of the chapter, but I just want to point out right now that this was his theory back in the day, but of course, with more modern instruments and the ability to actually measure atoms, well, then we know more now. Okay, so by the end of the 1800s, so as we go into the 1900s, we learn that that's not all. It's not just atoms that are the smallest thing in the universe. Instead, we find out that each atom is composed itself of subatomic particles. Specifically, starting with electricity, electricity is basically energy that comes from the flow of electrons, which are a very, very, very tiny, almost no mass at all particle that has a negative charge. And then finding out more particles later on, we found out about protons and we found out about neutrons as we entered the 20th century. That is the 1900s. And yeah, we found out that some of these subatomic particles have charge. Electrons have a negative charge. Protons have a positive charge. What do you think about neutrons? They're neutral, so they have zero charge. So real quick review on charges. So this is, the basic components of electrostatic force. You probably have learned this somewhere before, but it's always good to review. And one thing that we know about chemistry is that if we can understand positive and negative charges, then we're going to understand a lot of what makes a molecule either attracted to another molecule or not attracted to another molecule. It's going to help us explain a lot. So this is like one of the most important things that we can understand. Now, this is the easy part. The hard part is then in the future, we're going to have to predict where there's negative and positive charges on a molecule, but we'll get there in good time, don't worry. So first up, we know that two like charges repel. In other words, a positive charge will repel another positive charge. A negative charge will repel another negative charge. However, a positive and a negative charge will attract, right? This is the opposites attract idea, where these positive versus negative charges are going to try to come together. Okay, so that brings us to the first experiment that we want to learn about in this chapter, which is the discovery of the electron using what's called the cathode ray experiment. So a cathode ray tube, okay, this used to be easier to explain because it used to be that televisions were made out of cathode ray tubes. Maybe you have experience with this. I don't know, but maybe when you were like a little kid, you had like a big TV that was quite heavy. Like you wouldn't want to move it necessarily. And rather than a flat screen, it extended way into the back, and there's a lot of electronic equipment in there. Well, that's what we call a cathode ray tube screen, or a CRT screen. Same thing is true with computer screens, right? They used to be these very, very big, bulky monitors. Those are made using cathode ray tubes. So the same principle is here. Basically, a cathode ray tube is an evacuated tube that has a negative charge on one side and a positive charge on the other. And what J.J. Thomson noticed is when he did this, and he took, he made it into a vacuum in the middle, and he started applying voltage, he saw streams of particles coming by and hitting like basically like photographic paper, phosphorescent paper. It said, oh, hey, something's hitting me here. What's going on with this? Well, through experimentation, he was able to determine that they were negatively charged. Namely, you can use a magnet, either the north end or the south end, and you can see the way that the electrons would be affected by that magnetic field, and that would give you an idea that, okay, these electrons are negative. So this was the first subatomic particle that was discovered. Again, just for convenience sake, because it was negatively charged, it was easy to discover. Also, it's responsible for electricity. So anyone who was doing experiments on electricity, was using electrons. So all of a sudden, we have the model of the atom. And until then, we just kind of thought, oh, it's just these discrete particles, and each atom is made up of a different type of thing. So they were just the balls that we were looking at. Well, with J.J. Thomson now, he said, okay, well, part of the atom, the negative charge part of the atom, is the electron. Okay, And the rest of the atom, that ball, is just a smear of positive charge. So it's known as the plum pudding model, which might not make sense unless maybe you're British, and this does make sense. For the pudding is the positive charge, and the plums are the negative charge here. So it's like the kid stuck his thumb in the pie and got the plum. It's probably easier for most people in the world. I don't know, maybe it's just Americans too, but I think of it as the chocolate chip cookie model, where the electrons are the chocolate chips in the chocolate chip cookie, and then the dough of the chocolate chip cookie is the positive charge. Either way, hopefully that gives you an idea of what J.J. Thomson proposed as the structure of the atom. Now, but that's not good enough, right? Number one, if we have a particle that's responsible for the negative charge, why is it that the positive charge is just this smear of matter? We're finding more and more discretely, this matter is bound up into certain particles. So that's not a good explanation. So J.J. Thomson had a student named Ernest Rutherford who was working on discovering the structure of the atom. And what he did is he set up a radioactive experiment where he has a radiation source here that's in a lead container with just like a little hole here. So the only particles that are going to get out are like this. So it's like a radiation gun is the way you can think of it. And this is a beam of particles. We'll talk more about the types of particles here. They're called alpha particles. The key thing is that they are positively charged, okay? Very crucial, positively charged. Now, based on J.J. Thomson's model, if you shot a positive charge through this here, this weak, diffuse, positive charged pudding wouldn't be able to stop it. It would just soar right through. And so you'd expect, if J.J. Thomson's model of the atom is correct, you would expect 100% of the particles just to go straight through, like that. And you can think of it as like punching through, because these alpha particles have a pretty high speed. So they're not going to be stopped just by this diffuse positive charge. But in fact, when they did the experiment, that's not what happened. What happened was many of them did go straight through. So something like, I'm going to say 97% went straight through. But approximately 3% were deflected somewhat. So that says that, okay, they hit something that caused them to bend. And remember, these are positively charged particles. So what's going to cause a positively charged particle to move from its course? Well, another positively charged particle, right? There's a positively charged particle that's going to cause this to bend. And in fact, some of them even bounced back. So we'll call this like around 1%. I know those don't add up, but you don't need to know the exact numbers. You just need to know like a very, very small number actually bounced back. Or maybe I think it's like 0.1%. I should go with that instead. A very, very small number of these particles actually bounced back, and they were able to image them using the phosphorescent glow here. So, here, do we have the next one? So here's the theory, basically. This leads us to the Rutherford model, and we have the words for this on the next slide. So you don't necessarily need to write down what I'm saying, but the Rutherford model says that, okay, this alpha particle would not have been deflected unless we have a very dense positive charge. And he proposed that the center of the atom contains this dense positive charge, and that is what we're going to call the nucleus, which is, again, just the center of the atom. So then the electrons would be just in a cloud around the positive charged nucleus. And he was actually able to describe the size of the nucleus, because at that time, we had some ideas on the size of atoms based on other experiments. And based on, if you know the size of the atoms and you know how many of these particles deflect, you can get an idea about how small these are. And it turns out the nucleus is about 1/10,000th the size of the atom itself. So I've heard different ways to describe this, but if you think of like a big football stadium, so or I don't know, let's go with the Anaheim ballpark. If you have your baseball park, that's the atom. The nucleus would be the baseball, one baseball in the very center of that stadium. Just to give you an idea, the atom is very small, right? And then even smaller, almost inconceivably small, is the nucleus. So yeah, that's what Rutherford determined, is that we have a small positively charged region in the center that's got the nucleus. And then it's occupied by the region around it. The rest of the atom size is occupied by the electrons. Okay, so that brings us to the modern times, where we've got this structure of the atom where we have a nucleus, and the nucleus contains protons and neutrons. So we didn't talk about neutrons yet, but they're the third subatomic particle that we discovered. And like the name suggests, they are neutral. They have no charge, whereas protons have positive charge, electrons have negative charge. So the center, the nucleus, again, the tiny, tiny space in the middle, has both the protons and the neutrons. And the electrons are just kind of floating around in a cloud. And that accounts for the rest of the atom's size. So yeah, this kind of gives you an idea, right? So we take our strip of lithium metal, we look at it, okay, we envision these balls are these atoms. Then if we zoom in even further, on the order of 10 to the negative 10th meters, we have a nucleus in the middle, surrounded by 3 electrons, because this is lithium. And then in the center, we have our protons and neutrons for the lithium atom, and that's the nucleus. Okay, so those are our subatomic particles. I think we're going to talk about this next. Yes. Okay. Great. Okay. So good to just kind of like have that in your head. We're going to talk a little bit more about them and give them some more details here on the next slide. All right. So atoms are really, really small, right? So they're very, very light as well. They don't have that much mass, right? But now we're going to shrink down to the atomic scale. We're going to think in our heads that we're on the atomic scale and try to understand, how mass is distributed in an atom. And as it turns out, the mass of the atom is almost entirely due to protons and neutrons in the nucleus. Electrons have about 1/1000 the mass of a proton or a neutron. Now, because these are so small, rather than using a gram-based unit, we have a different unit that is useful on the atomic scale, which is called the atomic mass unit. So you can think of it like grams, but it's only useful on the atomic scale. And an atomic mass unit is defined as 1/12 the mass of a carbon atom, specifically a carbon atom that has 6 protons and 6 neutrons. So if you take that mass and divide it by 12, you end up with a proton having a mass of about 1 AMU, specifically 1.007 AMU. A neutron has a mass of about 1 AMU, specifically 1.008 AMU. So note the neutron and the proton are almost the same mass. Neutron's just very, very slightly more massive. And then the electron has a negligible mass, which is 0.00055 AMU. So when we consider the mass of the atom, we're not even going to worry about the electrons that are there. Okay, so yeah, so here's our summary of the subatomic particles in the atom. Like I'm for sure going to ask you this on the test because this is kind of crucial information. Now you don't have to memorize the exact masses here. What I always do is here, this is like about 1 AMU. The neutron also about 1 AMU, and then the electron is essentially 0 AMU. Now it does have some mass, but just not very much. So what else do you need to know? Oh, the symbols here. Yeah, this is useful. A proton is symbolized as P plus because it's got a positive charge. Neutron is N0 because it has no charge. And then an electron is E minus because it's got -1 charge. The protons and neutrons are in the nucleus, and the electron is in empty space outside the nucleus. Okay, so let's go ahead, get your sample exercise packet out, let's try to think this through, see if it's absorbed in our heads yet. Which of the following subatomic particles fits each of the descriptions below? And there could be, oh no, I think it is just, it's one per here. So A, found outside the nucleus. B, has a positive charge. And C, has mass but no charge. So which one fits that? Go ahead, pause the video, and we'll come up with the answer in a moment. We're back. So what's found outside the nucleus? Well, that's the electron. Which one has a positive charge? That's the proton. And which one has mass, no charge? Well, that's the neutron. The neutron's the only one that has no charge. Okay, which of these is true or false? So let's go through each of these for sample exercise 7, come up with true or false, and then we'll discuss it when we come back. So go ahead, pause the video, work on these, and we're back. So the mass of an electron is greater than the mass of a proton. Is that true? No way. That is false. Protons have a positive charge and electrons have a negative charge. Yes, that is true. And then the nucleus of an atom contains only the protons and neutrons. Yes, that is true. Okay, all right. So now we're going to explain the numbers that are on the periodic table above or below each element. So, right, so if we have the symbol Na, which element is that? Sodium, okay, and we see above it has this big number 11. That is what we call the atomic number. Now, we're just going to put this here. Atomic number, we are going to refer to as capital Z, okay? That's the atomic number. I know it's annoying or confusing, but as long as we kind of keep consistent with it, it's going to work out great. What do we notice about the atomic number? Well, for each element on the periodic table, it's always a whole number from 1 to 118. For every atom of a particular element, it's always the same. And what actually determines the atomic number is the number of protons that are in the atom. So, for example, sodium with atomic number 11 always has 11 protons in its nucleus. In other words, if you were in the wild and you found an atom and it had 11 protons in its nucleus, you would know right away, oh, that's a sodium atom because it's got 11 protons. You don't have to think about anything else. It's literally just a number of protons in the nucleus. That determines the identity of the element. And yeah, sure enough, it appears above the symbol of the element in the periodic table. Okay, so just to kind of like re-emphasize this, hydrogen, atomic number 1, every hydrogen atom has 1 proton. It's the only possibility. If you add in another proton, you don't have hydrogen. What element would you have if you have 2 protons? It would be the next one over, helium. Carbon, atomic number 6, every carbon atom has 6 protons. Gold, gold has atomic number 79. That means every single gold atom in the universe has 79 protons. Oh, and I just want to go, this should go without saying. Well, it maybe doesn't go without saying. Who knows? The universe is very weird. But protons, neutrons, electrons, they only come in whole numbers. You can't have half of a proton. You can't have half of a neutron or half of an electron. You have 1, 2, 3, 4, whatever. If you were to try to cut that in half, it would really blow up on you. So you cannot have like half of any of those. Okay, so note the whole number above the atom symbol, that is the atomic. Yep, okay, looking good. All right, so let's go ahead and do this now. Just make sure that we understand this well with atomic number. Sample exercise 8. Select the correct number of protons in each atom. We've got fluorine, potassium, and barium. Go ahead, take your time, pause the video, come up with your answer, and we'll go through it when we come back. Okay, what do you think? Are you ready? Fluorine, atomic number 9, has 9 protons in its nucleus. Potassium, K, that's atomic number 19. Each atom has 19 protons in the nucleus. And barium, that's Ba, atomic number 56. Each atom has 56 protons in its nucleus. Okay, so now we're going to go through a few different things that we need to know about atoms. Okay, number 1, atoms are neutral. That means that electronically they have 0 net charge. And what that really means is if the charge on an atom is 0, And we know that all of the positive charges are because of protons, and all of the negative charges are because of electrons. We know that then that if we were to take the number of protons and subtract the number of electrons, then we would have to get 0. This is for a neutral atom. And so what do I want to say here? Oh, this is the net charge. For a neutral atom, the net charge has to equal 0. So if you take the number of protons, subtract the number of electrons, then you get 0. So like, for example, if we have an atom of calcium, calcium has an atomic number of 20. So Z equals 20. Now, what does that mean? That means that the number of protons equals 20, right? Because that is the definition of the atomic number. Now, if we contain 20 protons, so let's just do the math here. So we know that 0 is going to equal 20 minus the number of electrons. We'll just add the number of electrons to the sides, and you get that electrons equals 20. Easy enough, right? The number of protons equals the number of electrons in a net neutral atom. Okay, so why don't you go ahead, give it a shot for sodium, zinc, and I guess I shouldn't. This is part of the quiz, right? Part of the exercise. It's Na, element Na, element Zn, and element S. Give me the atomic number, then the number of protons, and then the number of electrons in a neutral atom. Pause the video. Okay, and when we're back, take a look at the answer. Easy enough. It's just the same all the way through, right? Sodium has atomic number 11. So its nuclei have 11 protons each, and its atoms have 11 electrons each. Zinc, atomic number 30, has 30 protons in the nucleus and then 30 electrons to match them. Sulfur, atomic number 16, has 16 protons, and then to match that, 16 electrons. Okay, so we have the atomic number, Z. That's the number of protons. Now we have the mass number, A. Okay, and this mass number is going to be to represent the number of particles in the nucleus. Keep this in mind. This is for an individual atom. So we're going to write that there. And what this does is it represents the total number of particles in the nucleus. We know that the number of particles in the nucleus is equal to the protons and the neutrons, because those are the only two types of particles there. So the mass number, if we're putting this in terms here, is equal to the number of protons plus the number of neutrons for a given atom. Note, this does not appear on your periodic table. You do not see this on the periodic table. The thing that you see at the bottom there is what we call the atomic mass, and we'll explain that in a minute. The mass number is, again, only going to apply to single atoms. Okay, so what do we know? We know that the atomic number equals the number of protons. We know that the net charge of our atom is going to equal the number of protons minus the number of electrons. And for a neutral atom, that's going to equal 0. Oops. Okay. So, so that gives us like another thing that we can kind of look at here for an atom. Because here's the deal. Okay, first let's do a little math, and then we'll kind of drill into why we need the mass number. So if we take the mass number and subtract the atomic number, remember mass number is A, subtract Z, that's going to give us the number of neutrons. Think of it this way. The mass number is the number of neutrons plus protons. The atomic number is the number of protons. So if you take the number of neutrons plus the number of protons minus the number of protons, you're left with just the number of neutrons. So let's say it this way. A potassium atom has a mass number of 39, an atomic number of 19. To find the neutrons in the atom, what you do is you take the mass number, subtract the atomic number, that gives you the number of neutrons, which is 20 in this case. Now, here's the thing. Different elements can have different numbers of neutrons. So for example, I'll give you hydrogen. Like most hydrogen atoms have just one proton in the nucleus and 0 neutrons in the nucleus. So the atomic number for most hydrogen atoms would be 1 because you have one proton. But that's not the only type of hydrogen that's possible. There's another type of hydrogen that has a mass number 2, where you have one proton in the nucleus, because remember, it's hydrogen, it has to have one proton in the nucleus, but also an additional neutron in the nucleus. So putting them together, that gives you 1 plus 1, that's your mass number of 2. That's what we call hydrogen 2. And it doesn't stop just there. You can actually fit 2 neutrons in some hydrogen nuclei, which would give you hydrogen 3, which has 1 proton again, but 2 neutrons. Okay, so here we go. The number of protons is the atomic number. Great. The number of protons plus the number of neutrons, that's the mass number. So you get the number of neutrons is the mass number minus the atomic number. Yeah, we have all these equations in our notes. Make sure that you understand that. Okay, so here we go. So before we move on, let's go ahead and do just a sample exercise here to make sure we understand the numbers that we're talking about so far. So sample exercise 10, an atom of lead has a mass number of 207. The questions are, how many protons are in the nucleus? How many neutrons are in the nucleus? And how many electrons are in the atom? Keeping in mind that this is a neutral atom. So go ahead, pause the video, try to answer these questions, and then when we come back, we're going to have the answers on screen for you. So pause it. Let's go through what we know. Okay, how many protons are in the nucleus? Well, you can look up lead on the periodic table, and lead has an atomic number of 82. So the number of protons has to be 82. So you see, if I give you the atomic number, you can identify the element. And if I give you the element using your periodic table, you can identify the atomic number. Next up, how many neutrons are in the nucleus? Well, we know that the mass number is equal to the number of protons plus the number of neutrons. So if we take the mass number and subtract the atomic number, that should give us the number of neutrons, which in this case, 207 minus 182 comes out to 125. Finally, how many electrons are in the atom? Since it's a neutral atom, we know that we have to have the same number of electrons as protons. So 82 protons gives 82 electrons. Okay, do it one more time for sample exercise number 11. This is an atom of zinc as a mass number of 65. So go ahead, pause the video and answer these questions for A, B, and C. Okay, how many protons are in the nucleus of an atom of zinc? Well, it's always going to be 30 because the atomic number of zinc is 30. For this atom of zinc has a mass number of 65, how many neutrons are in the nucleus? It'd be the mass number minus the atomic number, which would give you 35. So 35 neutrons in that case. And then finally, what is the mass number of a zinc atom that has 37 neutrons? Well, in this case, you would take the atomic number, 30, plus the number of neutrons, 37, gives you a total of 67. Hopefully that makes sense. Okay, finally, sample exercise number 12. An atom has 14 protons and 20 neutrons. Okay, so give me the atomic number of the element, the mass number of the element, and then tell me what the element is based on that information. So go ahead, pause the video. When we come back, we'll have the answer. So go ahead, pause, and we're back. So we said 14 protons, right? That means the atomic number is 14. The mass number is just the number of protons plus the number of neutrons. So 14 plus 20, 34. Finally, what is the element? Well, we can look on our periodic table, find atomic number 14, that is silicon, or Si. Okay. Now, I used this word before, right? So this is, remember when we talked about atomic theory, Dalton's atomic theory, I mentioned something about isotopes. Hey, we're there. All right. So isotopes are atoms in the same element that have different mass numbers. And I mentioned this already for, you have hydrogen 1, you have hydrogen 2, and hydrogen 3, where you have 0, 1, or 2 neutrons, depending on the isotope. So again, they're atoms of the same element because they have the same number of protons in the nucleus. However, they have different masses because they have different numbers of neutrons in the nucleus. So again, same number of protons, but different number of neutrons. Magnesium, for example, has 3 possible isotopes. Most of them are magnesium 24, which have 12 protons, 12 neutrons. However, some of them are magnesium 25, which have, again, 12 protons, but 13 neutrons. And then finally, you have magnesium 26, which is 12 protons with 14 neutrons. Oops, what did I do? There we go. Okay. Okay, so now we are ready to talk about the atomic symbol or isotopic symbol. So this is how it always works. So we have the symbol of the element, which I'm just going to use X here to describe. We then write the mass number on the top left corner here, and then the atomic number on the bottom left corner here. So this is the symbol. This is the mass number. And this is the atomic. Okay, so this is the most common way that you'll write this as a way to represent isotopes, because there's all sorts of times when you need to write about isotopes. For example, if you're running radiology, one of the things that you need to know, and we'll talk more about this in the nuclear reactions chapter of the class, you need to know which isotope you're using so that you understand where the isotope is going to go in the body. For example, if you had radio-labeled iodine in your system, that would concentrate in your thyroid. So perhaps there's something in the throat that you have to image. That's going to be what's used there. Now, the other way that this is written sometimes is you write it as element dash the mass number. So like, for example, here, I mentioned already hydrogen 3. This is how we would write hydrogen 3 in this notation. We have atomic number 1, mass number 3, symbol H. Down here, how I would write it is hydrogen, the name, followed by the mass number, hydrogen 3. And then sometimes people will write it this way. You could just write H-3. That's easier to write when you're, for example, in a word processing program. You can write it as H-3. It's a little quicker. And finally, I just want to point out one last thing, which is, you may ask yourself, okay, if I know the symbol of the element, I know the atomic number. So can't I just assume that one? And sure enough, you can't. You could just write this as hydrogen 3, skipping the atomic number here, because the symbol, remember the symbol, tells you the number of protons in the nucleus. So you don't necessarily need to write the atomic number there. But go ahead and do it anyway, just for this class. I prefer to see it this way, and it'll set you up to communicate better with other people. Okay, so let's look at some examples here. If we had oxygen 16, it's oxygen, so we know it has 8 protons in the nucleus. As an atom, neutral atom, it has to have 8 electrons to match the 8 protons. Then the number of neutrons is just the mass number minus the atomic number, which is conveniently written for you here in an easy way to subtract. So that's 8 neutrons. About phosphorus. Phosphorus only shows up as one isotope. It's phosphorus 31. So we know it's phosphorus. That means it has to have 15 protons. As a neutral atom, it has to have 15 electrons to match the 15 protons. The number of neutrons is 31 minus 15, which is 16, et cetera, et cetera, et cetera. Okay, so why don't you go ahead and do this for the 3 different naturally occurring isotopes of carbon: carbon 12, carbon 13, and carbon 14. Write the atomic symbols for each of these isotopes, state the number of protons, neutrons, and electrons for each of them as well. Pause the video, fill out the table, and then we will go ahead and talk about it together. Okay, are we back? Okay, let's go ahead and give it a shot. Okay, now carbon 12 we already did, which is we have 6 protons matching 6 electrons, and then we have 6 neutrons as well, because 12 minus 6 is 6. Well, if we go to carbon 13, the only thing that changes is the number of neutrons. We still have 6 protons in the nucleus because it's still carbon. And the only thing that changes is we added 1 neutron. And we do it again, we get to carbon 14, which has 8 neutrons. So note what's the same about these. they all have the same number of protons because they're all the same element. Because these are all neutral atoms, then they have the same number of electrons. Only thing that changes is the number of neutrons. Okay, so go ahead next and give me the atomic symbols for atoms that have the following particles. For 8 protons, 8 neutrons, 8 electrons. What element is that? 17 protons, 20 neutrons, 17 electrons. And then finally, 47 protons, 60 neutrons, and 47 electrons. Go ahead, pause the video, and when you come back, we'll have the answers. Pause, and we're back. Well, if we have 8 protons, that means we have to have oxygen. 8 protons plus 8 neutrons is 16 for our mass number, so it's oxygen 16. Should just look like that. Do it again for B. B has 17 protons, so that tells us it's chlorine, symbol Cl. Next up, we have 20 neutrons. So 17 plus 20 gives 37, so it's chlorine 37. Okay, finally, we have we have 47 protons. So we look it up on the periodic table, atomic number 47. Sure enough, it's silver, which has the symbol Ag. And we know it's silver because of the number of protons. So we find the mass number, we just add the number of protons plus the number of neutrons. That's 107, so mass number 107 for silver. Okay, all right. So for the next sample exercise, let's go ahead and consider the pairs of atoms. X is going to represent the chemical symbol of an element. Looking at A, B, and C here. And you're going to answer 2 questions. Which of the pairs are isotopes of the same element? And in which of the pairs do both atoms have 8 neutrons? So basically what you're going to do is look at these symbols and ask yourself, okay, which of these are true isotopes? In other words, they're part of the same, they both identify as the same element. And then ask yourself, in which of these pairs do they both have 8 neutrons? So go ahead, pause the video. And when we come back, we will go ahead and take a look at that. Okay, so which of the pairs have isotopes of the same element? Well, in order for them to be isotopes of the same element, they have to have the same atomic number. So you have 8 and 7 here, nope. 6 and 6, yes. 7 and 8, no. So B is the case for this one here. Each atom has 6 protons, so the elements are going to be carbon. Next up, in which of the pairs do both atoms have 8 neutrons? Well, in A, we have 15 minus 8, or 7 neutrons and 8 neutrons. Here it's 6 and 8, and then here it's 15 minus 7, which is 8, 16 minus 8, which is 8. So it's got to be C that has 8 neutrons together. Okay, finally, we're ready to explain this other number that's on the periodic table that you're going to get confused for the mass number in the future, but don't do that. Put this in like a separate box in your understanding of what these numbers are. So we have the atomic number here, right? That's the number of protons in the nucleus. The symbol, no problem so far. And now at the bottom, we have the atomic mass. The atomic mass of the element is calculated based on a weighted average of all of the naturally occurring isotopes. So what we do is we go out into the wild and we sample, copper atoms, let's say, from various sources. And we find out on Earth how many copper atoms of this isotope do we have versus how many copper atoms of this isotope do we have. And based on that, we just take the average of those two, accounting for, let's say we have 25% of this one and 75% of this one. We're going to weight more heavily the 75% one to get this average number in the middle. Note, again, this is not the same as the mass number. Okay, so go ahead and look on the periodic table and give me the atomic mass of each of these here. Pause the video and you can kind of like go through it. But I'm not going to really spend too much time on this because you can always just look this number up. So like calcium is 40.08, aluminum 26.98 AMU, lead is 207.2 AMU, and barium is 137.3 AMU, and iron is 55.85 AMU. Oh, and I should have mentioned, the reason that what this atomic mass really does is, the way we can think about it is, it's basically the mass of an average atom. And this is going to be useful because when we actually deal with atoms, of course, we deal on like a huge scale, and these aren't purely isotopes of one or the other. So this is going to be useful on large scales. So like when we're in lab and we're calculating the number of atoms that we have to use the atomic mass to give us an average of the number of, an average of the mass of an individual sodium atom or chlorine atom, let's say. Okay, so that's that. All right. So most elements have two or more isotopes that will contribute to the atomic mass of an element. So like, for example, lithium has two isotopes, lithium-6 and lithium-7. Now, if you look on the periodic table, lithium's atomic mass is 6.941 AMU. Well, which one do you think is weighted more heavily in terms of the average here? Well, it's close to 7, right? So that tells us that lithium-7 is the most abundant isotope. How about carbon? Carbon has 3 different naturally occurring isotopes, carbon-12, carbon-13, and carbon-14. But we look on the periodic table and the average atomic mass is 12.01 AMU. That tells us very much so that carbon is very heavily weighted towards the carbon-12 isotope. Same thing with oxygen here, where we have 16, 17, and 18, but the atomic mass of oxygen is on average 16 AMU. So that tells us the most abundant isotope is oxygen-16. Okay, let's look at magnesium, for example. Magnesium has 3 occurring isotopes, 3 naturally occurring isotopes, magnesium-24, magnesium-25, and magnesium-26. So again, the only thing that differs here is the mass number for each of these, right, which is the number of neutrons. And then if we were to go out into the wild and like try to find the number of magnesium atoms that exist in, a given ore, let's say, and we just analyze how many are magnesium-24 versus 25 versus 26. Well, on Earth, it's about like this. We have 78.7% of our magnesium atoms are magnesium-24, 10.13% are magnesium-25, and 11.17% are magnesium-26. So because if we look here, almost 80% of the magnesium is magnesium-24, we should expect its atomic mass to be closer to 24 than 25 or 26. And sure enough, it is. If we look it up on the periodic table, it comes out to 24.31 AMU. So that's the mass of an average magnesium atom. Okay. Same thing with chlorine. We have 2 different we have 2 different isotopes that are stable for chlorine. We have chlorine-35 and chlorine-37. Well, chlorine-35 is about 3 times more abundant than chlorine-37. So the atomic mass is much closer to the mass of chlorine-35 than it is for chlorine-37. So here's how you actually would calculate atomic mass. You find out an experimental percent abundance for each isotope of the element. Then you multiply that percent abundance by the atomic mass of that isotope, and then sum the total mass of each isotope. So for example, the way you would do it for chlorine, I'm not going to ask you to do this on the test, but I might as well show you how to do this right now. So if we have 0.7576% chlorine-35, what we do is we express that percent as a decimal, 0.7576, multiply it by the atomic mass of chlorine-35, which is approximately 35 AMU. We could measure it more precisely, but there's no need to for us. And then we're going to do that again. We know it's 24.24% chlorine-37. So we take 0.2424 times 37 AMU, and we just add those numbers together. And when we do, that comes out to about 35.45. So that's how that number is actually gotten to. Now for us, what we're going to do is we're just going to kind of base it on, we're not going to actually ask you to do that calculation, but you will need to, if I give you an element with 2 isotopes, tell me which one's more abundant. Like here, this one we already did. So lithium has 2 naturally occurring isotopes, lithium-6 and lithium-7. The atomic mass for lithium on the periodic table is 6.941. Which isotope is more abundant? Well, 6.941 is closer to 7. That tells us lithium 7 is more abundant. Okay, final one here. And I think we're done after this. We got to move on to the next lecture. There are 3 naturally occurring isotopes of potassium, K39, K40, and K41. If the atomic mass of potassium on the periodic table is 39.10 AMU, which isotope is the most abundant? Go ahead, pause the video and tell me which one's most abundant and why. Well, if our AMU on average is 39.10, that's a pretty good indication that potassium 39 is the most abundant because this is heavily weighted towards potassium 39. Okay. All right, so that does it for our discussion of isotopes. In the next chapter, we're going to talk about the electron structure of atoms and then how ions. So very exciting stuff, and I will see you very soon. So until then, bye-bye.